let's say I have a string of zeros and ones, like 0, 1, 1 for example. And then I flip a coin until my string occurs. When do I expect my string to occur for the first time? This is a graph of how likely it is for my string to occur after n flips. The y-axis is the probability, and the x-axis is how many flips I had to make in order for my string to occur. As you can see, this function depends on what string I choose. The red one is for 0, 1, 1, and the green one is for 1, 1, 1. You can see that 0, 1, 1 is more centered around 0. It is more likely to happen faster than 1, 1, 1. This might seem counterintuitive, at least it did for me. And the explanation for why this happens is right here. Let's say I choose the string 1, 1, 0. And okay, so this means I will flip several times until I get 2 consecutive ones. Once I get 2 consecutive ones, there are 2 options. Either the next digit will be 0, in which case I am done, or the next digit will be 1. If the next digit is 1, then it's true that I didn't reach my string, but also it's true that these 2 digits over here are 2 ones. So that means that I got back to where I started. I got back here to these 2 ones. This means that once I get 2 consecutive ones in my flips, then I never lose these 2 ones. All that remains is to roll a single 0 for me to reach my string. On the other hand, when my goal is to get to 1, 1, 1, then the same thing until I get to 2 consecutive ones. And if I roll a 0, then this brings me back to the beginning completely. I lose these 2 ones. Now I need to roll 3 ones again. So this is the reason that this is an example of the fact that the probability curve is very much depends on what string I choose. Let's say we were to play a game. We both choose a binary string, and whichever binary string ends up comes first wins. Let's say you choose 1, 1, 0. You choose the string 1, 1, 0, which would be a good choice because the average number of flips you would need to get it is 5, which is the best possible, which is the shortest possible for 3-digit strings. If you would choose this, then I would choose 0, 1, which has the same expected number of flips. So you might expect that they would tie. Well, let's see. So we have the infinite string of flips that we got that we will get from the coin. And your string is somewhere over here. This is the first occurrence of your string. Now, if the digit right before your string were to be a 0, then my string would come in before yours and my string would win. This is only a rule of thumb explanation, but this is the mechanism behind the reason that my string would win 75% of the time. Here. Okay, so we have a lot of types of three-digit strings, and we can see that the way which one defeats which other one might not be that trivial, and definitely doesn't only come from this number of average flips when they are alone. So we have these correlation elements, and these correlation elements gives us this graph. This graph tells you which string wins against which other string. When an arrow points from one string to another, it means that this string on average wins against this string. So these strings are divided by hierarchy. The 1, 1, 1 and 0, 0, 0 have an average number of flips, and have an average number of 11 flips until they occur. 0, 1, 0 and 1, 0, 1 occur on average after 7 flips, and 0, 0, 1, 1, 0, 0, 1, 1, 0 and 0, 1, 1 occur on average after 5 flips. So what comes up immediately from this graph is the awesome fact that you have this circle right here, this loop. No matter which string from here you choose, I would have been able to choose another string from these four that would have defeated the string that you chose. Let's say you choose this string, then the string that defeats this string is this one. And the string that defeats this string is this one. And the string that defeats this string is this one. And so this game is a lot like rock, paper, scissors, which doesn't have a winning strategy. This is the graph for 3-digit binary strings, and it has the property that no string from low hierarchy is defeated by any string from a higher hierarchy. This does not hold true for 4-digit strings. In 4-digit strings, there's a lot of inter-hierarchical defeating strings defeating strings. The program that I made to calculate this, I had run it on larger strings, up to 5, and the code I have it up on GitHub. So if you want, you can run it as well, and it draws the graphs for larger strings, and for these graphs I had calculated how many cycles there are in each graph, and so here's the table. So of course for 1 and 2 digits you don't have any loops. For 3-digit strings you have one loop. It's what we saw right there. For 4-digit strings we have 12,275 loops, and for 5-digit strings my computer is still running I am now at 42 million loops, but it's gotta be more than that. So this number is definitely more than 1 million, and that's the number I chose for this video. I don't know what it is, but it's pretty damn big. That's it. That's everything. There's the graphs are pretty cool. They are all symmetric and stuff, so you can go check them out on my GitHub in the description. And that's it. Thanks for watching.